VR, that means you are continuing to work through this worksheet. So to flip this a little and put some work and a little more thinking and writing on your part. Otherwise, you're too passive, kind of just copying what I'm doing. So this is meant to flip that. So we've started working on CouetteFlow. And basic problem is that I have two cylinders. Inner one is static, and that one has radius kappa r. Outer one is the one that is turning around at a constant angular velocity omega 0. The relationship between the velocity in theta direction and omega 0 is essentially, in terms of the value, it's omega 0 r, right? And the direction of that velocity is, of course, tangential to this cylinder as I move around the cylinder. So I have the direction as delta theta, which is my coordinate vector in theta direction. Okay? So I have that set up, and because of this basically dominant boundary conditions, I have a cylinder. Everywhere around that cylinder, I'm imposing the same omega 0. That's how mechanically my setup is working. That's basically enforcing that my v theta, okay, which is kind of constant along the entire boundary, is also dominating both Vz, which is assumed short, so I don't have, my setup is not allowing, at least on that boundary, any movement down, because everything is moving with the setup, right? So on the boundary, I don't have dependence in Z for sure. On the static boundary inside, I don't have dependence for Z at all either. So any dependence of Z I would get would probably be inside that cylinder, which is relatively thin. Okay. So, and I'm also assuming relatively short distance, so gravity, even if it's acting, it's not overwhelming. So this is basically what's telling me that it's reasonable to assume that my v theta is the dominant one. And initially, we were saying, hey, v theta is v theta of r. VR is zero, nothing's moving in our direction, I'm okay with that. These are solid cylinders, so nothing is moving radially. And my Vz is likely a function of Z and R, but if I actually put these assumptions into equation of continuity, I'm going to get that Vz is simply just Vz of R. At that stage, I also assume, I look at this as like, okay, realistically, v theta is going to overtake this thing, especially since I'm imposing the same v theta along Z. So I'm going to basically ignore Vz altogether for practical reasons too, because otherwise we can't solve we can't solve this system if there are two non-zero velocity components, not analytically. So typically I have to, in order to be able to solve analytically, I have to have a system that I can reasonably simplify to the situation that only one velocity component is non-zero and it's dependent on only one other direction. Okay? So in this case, v theta is v theta of r. So now we actually, in this particular case, we could do shell balances on this, just like you've used. And for your own practice, I would just do that as a practice problem. But here we said, okay, we have equation of motion in its full glory. Okay, let's actually just go to the back of the book and apply equation of motion. Since this is theta velocity, I'm going to take the theta component of it, because equation of motion is a vector equation. So each basically vector component is directing, by the most part, one of the velocities in that particular direction. And so we go to the theta one, and we got, let me display it quickly because I do think it's important to look at it. So I have my midterm somewhere. Okay. So if I actually look at page in my book, it's 848, cylindrical coordinates. Okay. My B65 is what governs theta direction for equation of motion. What I see here is rho theta component of dv dt, where dv dt is the material derivative of velocity. Okay, so this is writing it out in full details in cylindrical coordinates. Okay? And equals to, then there's gradient of pressure component. Okay? And mu times, this is my Laplacian of velocity, it's theta component. Okay? And plus theta component of the external force. So however complicated this might look like, this really says mass times acceleration in the coordinate system moving with the fluid is equal to forcing in theta direction. Okay. So essentially, when we actually plug in our assumptions for v theta, so v theta is a function of r, this here is the only term that actually survives. Okay. So I hope you got to the point that in A, for this worksheet, you have calculated that this, when you simplify this equation, you get the ODE, and v theta is, if you start solving, the general form for v theta is a constant times r plus a constant divided by r. Right? And then I need boundary conditions. My boundary conditions are those on boundaries r and kappa r. Kappa r boundary, I know that my v theta is omega 0 r, r being uppercase r, right? And inner boundary is 0. Has everybody computed what v theta of r is in that case? Okay. So it is omega theta of r is omega 0 r, and then what? Uh-huh. Okay, everybody got that? If you didn't get that, can you write it down now? Because we'll use it later. So you can go and calculate it later yourself. But for now we need to, and I can project it. I'm gonna hook up my writing setup in a second, though I reinstalled everything, so hopefully it works today. But I am not holding my breath. So you're supposed to get this. Okay. And I did post these notes, I believe, for you. So once I basically solve the equation and put the boundary conditions, this is what you're supposed to, this is sort of a normalized way to put it, right? Maybe whatever you got doesn't look this pretty, but that's just a matter of writing it down.
What would you express it in this particular? What would you express it in this particular form?
Because I'm normalizing by kappa r, which is the inner cylinder. So I look at things, so this is dimensionless radius in a sense, where it's non-dimensionalized in terms of kappa r. Okay. Now it's your choice whether you're gonna normalize it by r or kappa r, right? So that's something that is up to the author. But looking at things in non-dimensional form, or some form that can be easily non-dimensionalized, is a typical way to go be more general. Because this system obviously scales with radius. Okay? So velocity itself obviously scales with outer radius, right? And the rest I'm looking in terms of, so if I was plotting this, I would also plot it against r divided either by uppercase r or kappa r. And note that difference between r and kappa r is not huge. So it's really up to you. So every time, because when looking at results, you want to look at a class of results as much as possible. And that is always, so in order to compare different results, you want to have dimensionless quantities. Okay, so now let's go to C, D, and E. So I'd like you to work on that. So simplify our equation. Let's now simplify both R and Z equations and see what we're going to get. I'm going to project them in a second. I think it's this one. So R and theta, this is my R equation. Again, a lot of terms will be 0. But it's not that everything will be 0. So just to see this time, why did I? Oh, never mind. Okay. So this is my R equation, this is my Z equation. Meanwhile, I'll try to set this thing up. By the way, I forgot to ask, does anybody need, I do have a couple of extra these worksheets. Anybody needs one? Okay. What did you get for simplifying the R equation?
Rho we take the square root of R dp over dr.
So I don't have velocity in R direction, okay? But I do have a pressure gradient, a bit of a pressure gradient. And this is this nonlinearity of the problem. And I like to picture it as things bouncing off boundaries. Okay? So I do actually have my dpdr is sort of balanced by the value of the velocity in theta direction. Okay? Even though I don't have the r component, okay, of the r. So that's an interesting, again, this is the nonlinearity of the problem. So if I computed v theta already, basically from my theta equation, that gave me v theta. So I can actually see what this dpdr, this pressure difference, is in our direction, even though it's not actually formally moving the flow in that direction because I have closed boundaries. So that's an interesting insight in nonlinearity of the problem. Did you do the balance for z direction? So that is hydrostatic pressure. I didn't need Navier-Stokes equation to talk about that. So that is essentially, that is there. And that is why often in shell balances we kind of didn't bother looking into these other equations because we would get a known expression for hydrostatic pressure. Okay, so now I am wondering what is the last question. And that is E. What is the force exerted by the fluid on the outer cylinder? we had a quiz on questions like that. If I had in my cylinder, here are the cylinders. Okay. I have an actually, well, I can actually imagine being here on the inner side. So basically, if I have a cylinder, there is a forcing, okay, that is exerted. So if I just had an area element on this cylindrical surface, okay, what is the direction of the force? Tangential to the cylinder, so it's in theta direction. Okay. And it is tau, we're talking about tau now, I'm integrating tau to get the force, right? Okay. So what am I supposed to integrate? If I just look at one element, okay, I have shear stress and I have area of that element. Shear stress, or the force itself, has a theta direction. But it's coming from r direction, or changes in velocity in r direction, because my v theta is v theta of r. So I have differences in velocities, and I have basically friction between different layers having different velocity, and that's what's transferring, and that's what's exerting this shear force. But the momentum itself is going in our direction. So what do I need to integrate on this area element of the outer cylinder? Tau r theta, right? Do we all see that? So that is basically, so locally on that one element, I just multiply tau r theta times the area, and I know what is in cylindrical coordinate system, what is the area, r d theta dr. Okay. So basically I multiply tau r theta with r d theta dr, and then I just have to integrate over the entire cylinder. That force does have a direction, okay? And it's actually a vector. I'm integrating a vector that has d theta or delta theta direction. Let's first, so start writing while I pop up. But basically I want you to write down what is tau r theta. Or what is the force, rather, in terms of tau r theta, while I pop open my sketchbook. The moment of truth to see. So my tau r theta, pre-installing didn't help. I'm going to continue writing the way I always do. So my tau r theta is force in theta direction exerted by the fluid. That these layers of fluid in what we call lower r direction are exerting onto the surface that is in higher values of r directions. Which, if I'm on the outer cylinder, I'm precisely oriented with that coordinate system description. Okay? So if I'm looking at the force, right, my fluid is in lower r with respect to my outer cylinder. And then I'm basically, if I'm looking what is fluid doing to the solid, it's aligned precisely with the definition of tau r theta. So all I need to do is multiply tau r theta with the area of the element. For the inner cylinder, I would have to do a minus, because my coordinate system doesn't know where the fluid is, and my coordinate system counts with tau r theta being of something, whatever is in the lower r directions, acting on something that is in the higher r directions, because that's in the direction of growing r. Are we clear on that, why we need a minus? So that was the exercise. So for outer cylinder, I'm good. So basically force in theta direction of fluid in, or anything in lower R direction onto higher I. Sorry, I actually reinstalled this software just before coming here, and apparently it's not helping, but. So basically, if I'm looking at the force on a surface element, so if I have outer cylinder, then force is tau r theta, okay, evaluated at r is equal to r. Direction of the force is delta theta, because force is in theta direction. And the area of this element is r d theta. So that's simply the area of that element. If I was working on the inner cylinder, I would have a minus, and my radius would be kappa r. Okay, so tau r theta would be evaluated at kappa r, and also that area of the element would be kappa r dr d theta. So basically, if I wanted the entire force, I would just integrate that. Okay. Now let's actually look into the torque. And what is torque? Because that's what's helping us here. So we could go and now compute this entire area, but I'm actually interested in figuring out how to get the viscosity out of this and how to actually compute it, and using both analytical expressions and what I actually have as a setup in the lab. So what I have as a setup in the lab is the fact that, hey, this element, so the entire system that is rotating, okay, what I'm controlling here is torque. And torque is basically ability or something to rotate. And I will typically look at it as a cross product between the arm, whatever is rotating the system, from the center of rotation, right? So arm, this would be my vector from the center of rotation to the tip of it, and times the force that is working against. So essentially, I would do a curl of that arm and the actual force. Okay? So I can compute here, since I know the force, okay, I can actually compute analytically this torque. And I can compare it to whatever was calibration in my lab to keep this rotation constant. So I can just assume that from the calibration of this system, I actually have torque already, because I'm rotating thing at velocity. So I'm going to now compute this torque. You can go and actually compute the force, so you can just do this integral, but what we're actually going to do as an exercise right now is to compute the torque, okay? And that will actually, that's what's typically given the values of viscosity for this system. We're going to see how we compare those formulas. So,
how is it that the tau RZ, I thought the tau RZ acted on a surface that was like on the outer surface, which has, I think, unit elements r d theta dz.
Yeah, this would be
but this is in theta direction. Dz, yes, dz. What did I write? dr. I already have an r in there. Let me now try here. D theta dz. Yes. Sorry about that. All right. So let's look at the torque. So we will practically, so you can go and integrate this as an exercise just to see what is the total force. What I will proceed and actually do a little more difficult thing, and that is the torque. Simply to comment on how do we actually use this system to find the viscosity. So this is a tendency to rotate an object. And sorry about the handwriting, but tendency of force to rotate an object. So if I have sort of this is my rotational path, and this is the what I call an arm of the force, and this is my force. Then torque is actually given as R cross F. And this is a cross product. And we know that cross product is a vector. It is a vector. Results in the direction that is orthogonal to the two directions that are here, or to the plane defined by the other two vectors. So in that sense, I'm going to get, in this case, my torque will actually point in the axis of the rotation. Right? So if I'm rotating this object around an axis, the torque points in that direction. So in this particular case, okay, if I'm actually doing the total torque, what am I going to integrate? So if I actually want to integrate to get the total torque, and I'm going to call it T, total in outer cylinder. So my force is tau r theta of r on every element, right? So now on an element of area element, this is the force. Okay? Now I gotta do a cross product. What is this arm on the outer cylinder? This vector r. It's r, and what is its direction? Delta r, right? So it's r delta r. You okay with that? And now I have to, that's my torque on that one little element. Now I have to sum all of those up over the entire surface. Right? So I'm going to integrate. My dz goes from 0 to L, and my d theta goes from 0 to 2p. Are we comfortable with the process? And again, for your own practice, you can just do the total force, in which case you don't have this term. Okay? So my z is simple, nothing depends on z, so I'm going to assume this length L, so that integral is easy. So that part is L. And basically then I have, what is my dependence? So my key thing here, so this, I need to figure out what that is. Okay. And the second part, so I'm just gonna do 0 to 2p. R square is also out of the equation. So I have tau r theta of r, which I need to plug in to figure out what it is. And I have delta r cross delta theta, d theta, dz I already did. What is this cross product? Coordinate vector, so it's the third coordinate vector, delta z. That one is constant. Right? Because if I had to integrate delta r actually changes, right? And so this is something to think about. Delta r is a function of theta and r. Therefore, I can't just grab delta r and put it outside of this integral. I gotta integrate that vector. Wasn't that a homework exercise or something, the vector calculus part? So when you get like delta r, delta theta, don't just put it out of the integral the way you would in a Cartesian coordinate system, because delta x, delta y, delta z are always constant. You can always pull them out of the integral and just do the integration of the rest. No, you actually have to then express it in terms of something that is constant. So you can actually go and express it in terms of delta x, delta y, delta z that are constant. And you will get functions of r and theta that you need to integrate. Am I speaking Croatian today? Is everybody connecting to this? Okay. A little bit of foreign language doesn't hurt. Anyway, so I hope it's not that boring. But you have to be careful with these integrations when this vector that you're integrating is actually depending on, in this case, theta. So I can't just integrate it that. But since this is always for any location around my cylinder, like delta r and delta theta are themselves changing as a function of r and theta. Okay. They point in different directions as I'm moving around the cylinder. However, no matter the location, their cross product is delta z. Again, so that part is actually easy. Huh? It's constant with respect to theta that I'm integrating over. Okay. So all I need to really figure out what is my tau r theta of r and integrate that. So what is tau r theta of r? How do I get that? Find it where?
Appendix.
Great. A little more specific, open up appendix. Minus mu r ddr, something like this, plus 1 over r dvr d theta. Okay, vr is 0, so this term goes away. This I computed v theta, so how about you all do a quick calculation of what this is? An integral of d theta will be 2p. So all I need is this value, really.
Dr. Bernard,
Yes.
just a quick question. So, why do you have the R times delta R? Just curious.
R d theta dz?
Or the R T, the R delta R. Maybe I'm not saying the right sign.
It should be R d theta dz. This one, R delta R,
Yeah.
that's this. At the outer cylinder, its length is R, and it's pointing in the direction of the R coordinate vector.
Oh, so basically.
At every point on cylinder, this is changing.
Okay.
So this term, let me grab this is this. Yes?
Oh, so you're.
On outer cylinder, when I evaluate the arm of the rotation,
Oh, so the torque formula is force times radius.
for whatever it's rotating, and this outer cylinder is rotating.
Oh, okay.
And its distance from the center is capital R, and it's always pointing in the R direction as I'm moving around the outer cylinder.
Okay, so not only are you specifying the amount of direction that the torque is pointing. Okay. So
And I gotta, so for the area element I'm trying to reach, it's at that element I evaluate delta R, which is my coordinate direction, and I multiply it by this length, which is R.
Okay.
So it's a vector.
Okay.
And then I move over here, and that's different vector, it's different delta R.
Okay, but it's still
Its length is still R.
Okay.
So it's always pointing in our direction, which is changing as I'm moving around the cylinder.
Okay.
So, and I have to integrate for every little element. So this is basically expression for one area element of the outer cylinder, wherever that element is. And then I'm summing up contributions of all of those, which is integration.
Oh, yeah.
When I integrate, I'm just summing up all of the contributions.
Right.
So this is just, again, this is expression for the area. This is delta theta, this is actually direction of that force. Okay? So let me find another color. So this part is the force. Okay? And this here is area element. Area. I'll just leave it as area. Yeah? And then I sum up all of those contributions. And the main problem is that if I were just, there's a cross product here, but if there was just delta R here, this is something that depends on theta. It's a function of theta, where I'm at the cylinder. And therefore, I can't just pull this coordinate vector outside of the integration, which is what I'm typically used to doing in Cartesian coordinate system. I see a constant vector and I move it up. Can't do that. However, luckily, delta R cross delta theta is always delta z. It's the third coordinate vector. And that one is always constant wherever I go.
Okay.
So I can actually pull it out. So I don't really need to integrate anything. It's 0 to 2. I mean, the theta, that's just 2p. That's where this 2p is showing up from.
Okay.
Right? But I need, what is this? And this I know from formulas. This is in appendix, I believe B1 in cylindrical coordinates. So if we have velocity field, which we calculated to begin with, okay, then this is my expression for tau r theta.
Okay.
Is everybody clear? It's quite a bit of writing actually. I'm kind of skipping some steps. But I'm letting you at least compute this. And I hope you get at the end something like minus 4p mu omega 0 r square L, and then kappa square over 1 minus kappa square delta z. So this magnitude, well, actually the entire thing, I actually know this because I'm rotating the system in the lab. I know how to calibrate that system. So from calibration, I know what this is. And R is constant, L is constant, kappa is constant, omega 0 is constant. The only thing I don't know is mu, so I can compute mu. Okay? So I know this, again, I know this. I know. From calibrating the system. So that allows me to compute mu. And again, it should come as no surprise that often to actually do a measurement, you have to assume a model and have an analytical solution to that model, which is what we have here. Okay. And on the other side, you have something to measure to compare with, and you equate the two. But you have it from a different type of, this is just from simply calibrating this mechanical device that is rotating things at constant velocity. Okay. So from that, and knowing the materials that go into building the system, you can calibrate that part and make it equal, and that allows you to make the measurement. So this is value of having a theoretical model. And whenever we are doing measurements, we have some assumption and simplified theoretical model that is built into it, right? So there are also some assumptions that you make along the way, which we gleefully ignore many times, okay? So as we were developing this solution, we made a whole bunch of assumptions that actually allowed us to compute this, okay? We ignored VZ, we ignored the gravity part, right? So there are certain assumptions we made to allow us to compute this. So there are some errors in that process. Okay. So make sure that you understand that nothing is perfect to a T. Okay. All right. Moving on. So now I'm just gonna start very briefly, introduce creeping flow around the sphere. We're not gonna solve it. I promise to skip that this year, which would take basically a week and a half to 2 weeks to actually fully develop. But this is one case where I'm just gonna introduce what the problem is, and then we're gonna work with formulas, because one formula that I do want you to know is Stokes' formula for the force of the fluid on a sphere inside of that fluid. Okay. So that is something that is practically used in a lot of applications, as it's important to know. But I'm just going to kind of introduce the complexity of the problem if we were to go and solve it analytically. Okay. So creeping flow around the sphere, or any sphere, is of interest in a lot of applications. You could think about a granular medium composed of sand grains. When you're flowing through a granular medium, you're essentially flowing around those grains. Not just one, but multiple. Okay. Second thing, we have particulate flows. So we might actually have fluids, like drilling fluids, that have particulates within. We could have formation damage that is happening, so some of the grains of the original porous medium are chipping off and flowing with the fluid. So then you actually have flow around those grains. There's propants that we're introducing to prop hydraulic fractures, so they have to be flown in, so we need actually expressions on how they move, and so forth. Sand production is actually formation damage that I mentioned before. So if I was actually modeling a problem, just one single grain, and I was looking at a projection of it, so here is a grain or a spherical particle. And let's say that I'm assuming that I'm moving so that far away from the sphere, I'm actually just moving in a single direction. Okay? And it's going to be z direction for my case. So as I'm introducing this grain, far away I'm vz, but when I get to the grain, I kind of have to flow around. Okay? As I'm flowing around, suddenly from just having vz, I'm developing both other velocities, okay, to flow around that sphere because I'm curved in all directions. And while I can assume that the way I slice this sphere is the same no matter what angle I take, right, I'm still going to get two velocities by flowing around those spheres. So that's a problem. So I can't have that just one velocity is non-zero when I'm moving around the sphere. So that's essential problem. So I need spherical coordinates. So just as a brief review, I have x, y, z, my Cartesian coordinate system. In spherical coordinates, my point is described by the radius, which is distance to the origin. Theta, which is this angle from my north pole, if you will, of a sphere, right? So z direction. And then phi, which is a projected coordinate, which I actually know from the cylindrical coordinate system. So when I project the point into xy, then I have a phi is the angle that I'm enclosing with the x-axis. So I have an angle with x-axis and with the z-axis. Okay. So my relationship to xyz is x is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. Okay? So if I'm actually interested in how my partial derivatives are related to each other, or how the coordinate vectors were expressed in terms of each other, okay, I can also look them up in Appendix 6. So again, I like visualizing this as these are my r theta phi coordinates, and then there's a matrix here. These are the elements of the matrix, okay, in terms of theta and phi that are multiplying delta x, delta y, delta z. Okay. And inverse, or actually it's just a transpose of that matrix gives me the inverse relationship between delta x, delta y, z, and delta r, delta theta, delta phi. So I have the relationships. I can go back and forth of the coordinate systems, but because of this curvature of the coordinate systems, I see now that my partial derivatives are quite a mess. Okay, so just always remember just to look it up. Don't memorize these by any means, but remember to look it up if you need to. So now we can, again, in this system of flowing around the sphere, I can safely assume that however I slice it in terms of this phi direction, okay, if I'm flowing in this direction now around the sphere here, if I slice it this way, that way, as long as I'm going through the center, I'm going to see the same picture of going around the sphere. So that much symmetricity I have, so I don't really have dependence on phi. Okay. However, I do have a dependence on how far am I from this center? Okay. Am I here, here, or here? And also, where am I here in terms of theta? So theta is this direction enclosed from z towards the point. So whether I'm obviously here, or here, or here, or here, it depends, right? So I have both r and theta dependence. Okay. So my VR is VR of r and theta, and my v theta is v theta of r and theta, and I can assume that my v phi is 0, okay, and I don't have dependence on z. So I have two velocities, okay, in order to go around the curved object like that is curved in two orthogonal directions. I have to have two velocities in two orthogonal directions. That's what it comes down to. Cylinder is curved only in one direction. It's not curved in the direction at all. So I have only one direction of curvature, so I can get away with only one velocity moving around, which was v theta. Right? But to go around the sphere, my sphere is curved in two orthogonal directions, however I turn around. So therefore, I need two orthogonal velocities to describe that if I'm trying to move around an object like that. And that's the complexity that I can't get away from. So I can figure out what my boundary conditions are. I have this far away from the sphere, so I will have the boundary condition of I would have the boundary condition of the type that as r that goes to infinity, I'm going to approach this infinity velocity that I see when there's no sphere. Okay. But it's still, and then I have to basically translate whatever I see that in my z direction, I have to translate that to my spherical coordinate system if I were solving a spherical coordinate system. I would have no slip on the sphere that I also have to express in spherical coordinates, and I would have no mass transfer into the sphere. So boundary conditions I'm familiar with. Those are the same type of boundary conditions that I would work with normally. So basically, if I was translating this coordinate, this v infinity velocity, okay, I know that it has a z direction. So if I was translating it to the spherical coordinate system, I would do VR, v theta, v. See, is that matrix that goes back and forth between spherical coordinates and my xyz coordinates, right? So this is how I would get my basically boundary conditions for VR and v theta. I think by now I convinced you that it's a pretty complex problem. Okay, so this is basically I would get my VR and v theta that way when I do this calculation. Okay? And I have that my v theta and VR have to be fixed on a sphere. So that much is fine. Okay, so if I was looking at the equation of continuity in motion, okay, then I would look at that appendix of mine that I had open. There we go. That one. So now I would go to spherical coordinates. These are the same equations that we looked for cylindrical and spherical. Okay. Since VR and v theta are non-zero, okay, I would have many more things that are not vanishing, and moreover, VR and v theta would be coupled within the same equation. So basically, breaking them apart and solving for them is essentially impossible the way it's supposed. Now, Stokes had an idea, and I'm not going to go into more details of it. This is just to show you how complex it can be if I have two non-zero velocities that I cannot further simplify. So I can't just, other than having a simulator, numerical simulator that would simply take this, I can't go use this equation of motion directly to solve analytically. There is an entire, it's called streamline approach, okay, that is there. It's not necessarily simple, and again, it would take us a week or so to derive. And Stokes in 19th century did not have a computer to plug this in. There was no COMSOL software or whatever software to actually work with. So he had to think hard at what would be a possibility to solve this analytically. And he came up with it. It's not necessarily a simple idea. And it's not a simple idea because he basically assume there is vorticity. There is a way to eliminate pressure from the equation because I have VR, v theta, and pressure that are coupled, and figure out, hey, if I take curl of a gradient of something is always zero. So I can eliminate the pressure by taking curl of the equation of motion. But that gives me a higher order equation in velocities. So then solving for it is still not super fun, but it's doable. I'm gonna just stop it at that, and we're just gonna work with ready-to-go formulas for Stokes' law.